Okay, good morning, everyone. I want to welcome you to another multivariate statistical class. Of course, today the focus today, I'm actually going to be focusing on variance of treatment effect difference. This is where we stopped yesterday, and I promise I'm actually going to start from here. Yesterday we started inferences about multiple mean vectors. And of course, I remember I walk you through the one-way analysis of variance for univariate and for multivariate extension. Of course, today, after we're done with the variance of treatment difference, I'm also going to walk you through two-way multivariate analysis of variance. Well, let's first start with the variance of treatment effect difference. Uh, what is the significance of this in statistical world? I'm actually going to say that this very essential when it comes to hypothesis testing involving mean vectors. If I want to construct hypothesis testing, I want to conduct hypothesis testing around mean vectors, or I want to construct a confidence interval, okay, of the difference of mean vectors. Of course, I actually need this variance, the variance of the difference. So if the variance of the difference is very small, then that will lead us to having a very huge statistical power. That's a gain in statistical power when the variance of the difference of the treatment effect difference is very small. Because don't forget, when you are looking into the weeds of confidence interval, when the variance is small, the width is going to be very small, and I mean narrow. When it is narrow, then of course you're actually going to have a very precise interval. So I'm going to say that the variance of treatment effect difference is very crucial in statistical finding, particularly statistical inference. Number one, it enables us to statistically test how significant is the mean vector, okay? And number two, it enables us to have a more precise confidence interval, because we realize that when the variance is low, of course, there's more statistical, there's high statistical power. What do I mean by high statistical power? The probability of detecting true difference is going to be high, which is what we want. And let me also say this. It's improve on the power of a test. Okay, so because uh, you actually really want to see whether there's a statistical significant difference between the mean vectors and the hypothesized value, something that is beyond chance. Now, let's take a look at uh, the the variance of the treatment effect I'm talking about. This is what we mean. This is what we mean by treatment effect difference. Okay, we're talking about the difference between the overall mean and the group mean. That's what we call treatment effect. We really want to see. So if this is treatment effect, then we need a variance for this treatment effect. Why do we need variance for this treatment effect? Because we're actually going to have a lot of this. It's going to, varies. It's not just going to be only one. Okay, there's going to be variations among the treatment effect estimated. And because of that, we want to find the variance of that. And don't forget, the variance of this play a very crucial role in the pool variance that we use in the Ottolenghi squared, and so on like that. and also play a very huge role in the construction of confidence interval. Okay, so now, and not only that, this enables us to adjust for correlation among response variables, because the correlation, if there is this a correlation among response variables and we ignore that, then we actually going to mislead. We don't want to mislead. Okay, so as I was saying, this guy is a group mean. When I say group mean, what is it, the mean of the response variable in a particular group? Why this guy? The overall mean. Okay, so when you are subtracting that, we are estimating a treatment effect. And that is the reason why in analysis of variance, we normally want to test if this treatment effect equal to 0 or not. Okay, so we can derive the variance, and for also be able to have that kind of test, then we need the variance of this difference. Okay, that's why it's very crucial. Now, take a look at what I'm showing now. Oh my God. If you take a look at this now, I actually want to find the variance of the difference of estimated treatment effects. So the variance of that, okay, is actually going to be this. And the sigma jj here is the diagonal element of our covariance matrix. Okay, the diagonal element of our covariance matrix. Now, let me now tell you this. If I'm able to have this in place, then I can conduct statistical inference. I can construct confidence interval, and with a precise, with very high precision. When I say constructing confidence interval with a very high precision, actually means I'm expecting that the variance of this difference is very, very small. Okay? Or before I can take a decision regarding statistical hypothesis, before I can say there's a statistically significant difference between mean effect, then it means the variance of the estimated treatment effect is very, very small. Because if it is not small, then you're going to say, even if difference exists, but that difference is not very much pronounced, which means you are not ruling out chance. Okay, so moving forward, now that we have the variance of the estimated of treatment effect treatment effect in place, we can now construct confidence interval, whether by way of Bonferroni or by Ottolini square and so on like that. So now take a look at that. Now the Bonferroni is just going to come in. Let me tell you this. Without Bonferroni, this is going to be, okay, let me say this. Why do I need a confidence interval in this case? When you conduct analysis of variance tests and the known hypothesis is rejected, what is the next thing you normally do? You normally go for multiple comparison. You want to know where the difference lies. Does that make sense? For instance, I have 3 groups and I want to compare means. Maybe I'm talking about plant growth. I'm talking about plant growth, and maybe my response variable is the height, the plant height. Okay, the plant height. Okay, and of course, the factor that I'm considering, maybe the type of fertilizer. The type of fertilizer. Maybe I got 3 levels of fertilizer. Because I got 3 levels of fertilizer, we got 3 groups. Level 1, no fertilizer. Level 2, organic fertilizer. Level 3, chemical fertilizer. And you know what I want to do? I want to compare the means in these 3 groups. If I conduct univariate analysis of variance and I reject the non-hypothesis, then we normally, ANOVA does not have ability to tell us where the difference lies. But ANOVA can tell us there exists a difference. If you want to know where the difference lies, then you need to actually go for, there's something that we call a post hoc test that we call multiple comparison. Now, it means if I have three groups, I'm actually going to if I want to know where the difference lies, I'm actually going to compare the two groups one at a time. What is the possible numbers of groups am I likely going to have? Is G into G minus 1 over 2. How do you think they derive that formula? It is G combination 2. How many ways can I select 2 out of G numbers of groups? That will be G factorial. Okay, if you use combinatorial analysis, divided by G minus 2 factorial, G minus 2 factorial, okay, then 2 factorial. Okay, now G factorial is the same thing as G into G minus 1, okay, G minus 2, okay, factorial. Why do I go to G minus 2 factorial? Because I wanted to cancel the denominator. So G minus 2 factorial. And what is 2 factorial? 2 factorial is 2. So this guy cancel this guy. And that was how we got this. That was how we got G into G minus 1 divided by 2. That would be the number of pairwise comparison. And let me tell you this. If numbers of group is large, the numbers of pairwise comparison is going to be large, which means you're actually going to have, so many tests. And the fact that you have so many tests, okay, if you want to do that one at a time, the probability of type 1 error will be exceeded. Okay, we don't want that to be exceeded, and that's why we need a control, we need an adjustment, and that's why Bonferroni is coming in. So what the Bonferroni is going to do is going to divide. Okay, please pay attention. So what the Bonferroni is actually going to do is to divide the numbers of that comparison. Take a look at this. Okay, I said we have this guy. Okay, G into that. Okay, to have the control is going to be Q. Q equal to Q. If we assume that P, if P equal to that, then in the Bonferroni, we don't forget we are dividing the level of significance by that 2Q. And where Q equal to PG, G minus 1 divided by 2. That is having a control. That is restricting the level of significance to 5%. Okay? Now, that is the Bonferroni that I just talked about. Now, when you have that, it's Bonferroni. Okay, now this is the coding now. If I want to do MANOVA means now, MANOVA, motivated analysis, why, when do we go for this? We go for this when you conduct one-way motivated analysis of variance tests and you reject H0. When you reject H0, then you now need to figure out where the difference lies. Then you conduct a multiple comparison test. Now I need you to pay attention to what the comparison test that I'm actually talking about. Okay, now when you take a look at what I have here, okay, if I'm talking about weight as a response variable, we get a lot of response variable. We're going to do one at a time, okay, and then here in the data set that we're using, the categorical variable is cylinder levels 4, 6, and 8. Okay, these are the LS mean. This is the standard error for that. And of course, we have both the lower bound and the upper bound. But there's something I really want you to see. Give me 1 second. Now, this is a comparison. Now, I'm putting into consideration the Bonferroni now. Take a look at that. You remember the other time? Alpha is going to be alpha over 2Q You remember what I said? Now, if I want to use macaroni, what am I doing here? I'm comparing two groups. Okay? This is the estimate of the difference. This is the standard error. This standard error is the square root of the variance effect difference that I talked about the other time. Now, do you know the meaning of this? What is it telling us? Oh my God. Positive to positive means different actually lies between four engine and six engine. When you are from the if you are from negative to positive, no difference because it's zero lies. Negative to negative, no difference. Does that make sense? Positive to positive, there's a difference. So what I'm trying to tell the world right now, please pay attention. Okay, this is a post analysis, post hoc test analysis conducted after the null hypothesis has been rejected in the multivariate analysis of variance. So if you take a look at this guy now, talking about MPG, okay, if you take a look at this guy for MPG, there's no statistical difference between six-cylinder engine and eight-cylinder engine because the lower bound is negative and the upper bound is positive, so zero lies in the interval. Now, we're doing simultaneous. Don't forget, simultaneous. This is the one for MPG. I'm also going to go to the one, for the other one. So this is for MPG. For HP now, I'm also going to do the same. Look at that. Okay. I'm doing the same for HP. Don't forget, you got more than one variable, one response variable. Okay. Now, this is going to give me an opportunity to be able to see where the difference lies. Okay. After the null hypothesis has been rejected in the multivariate analysis of variance. Is there any question about this? Go ahead. Yeah. In my decision, please pay attention. Based on your question, right now here, no difference. Negative to negative. Okay. Oh, sorry. What am I saying? Negative to negative, there is difference. Okay. Why do I say there is difference? Negative to negative, no zero in the interval. Whenever there's a zero in an interval, a zero in the interval means there is no difference. No zero in the interval means there is a difference. So if I want to know whether there's a difference, negative to negative, there's a difference. Positive to positive, there's a difference. Negative to positive, no difference. Does that make sense? So when I'm trying to tell the world now, okay, as far as HP is concerned, okay, there's no difference between four and six cylinder engine. Okay, so if you take a look at it, 4 to 6, no difference because the lower bound is negative, the upper bound is positive, zero lies in the interval. So because of that, the difference is not statistical significant. So no difference. But if you take a look at if you take a look at this, if you take a look at this, there is a difference. 4 and 8, 6 and 8, there is a difference as far as this variable is concerned. But if I go back, let me go back to MPG, okay, here, different exists. Here, different exists. But here, no difference. Does that make sense? Okay, so we're going to continue now. Now, what we just finished is how we can, it's a post hoc test, adjusted Bonferroni. Of course, you know why we actually have a Bonferroni correction is because there's going to be so many tests that we're conducting simultaneously that could inflate type 1 error rate. And in order to bring type 1 error rate under control, we need a Bonferroni correction. And the moment we have a Bonferroni correction, we can simultaneously have a pairwise comparison test. And in the pairwise comparison test, what I just show you, I show, we make use of the intervals. So where the interval contains zero, no difference. That is from negative to positive, no difference. But from negative to negative, there is a difference. Positive to positive, there is a difference. Does that make sense? Now where we're going now, you know, uh, we want to use module to depict reality. And the facts remain that module cannot give us exact characterization of reality. There's always going to be an error. And that's why in every statistical model, we have assumptions. So multivariate analysis of variance tests also rely on some assumptions. And these assumptions actually revolve around the error time. For instance, one of the assumptions conducting multivariate analysis of variance is that the variances have to be equal. The population variance, okay, for each group, all the group have to be equal. If they are equal, of course, whatever decision that we're going to take with multivariate analysis of variance tests will be valid. But what if they are violated? If they are not equal, okay, if they are not equal, and we ignore that, and we still pursue the test, okay, using the assumption underlying, using the assumptions of constant covariance matrix, then whatever decision we take will be invalid. It's not as if our models are failing us. Our models are not failing us, but we are the one that we're not doing the right thing. When you ignore assumptions, okay, what make model to be great is when assumptions are met. Okay, now, if we want to be sure, okay, and don't forget, if we want to be sure if this assumption hold, then we need to conduct a test, which is what I want to show you right now. Testing the homogeneity of covariances assumption, because the homogeneity of covariances is assumed when you were in the multivariate analysis of variance tests. Now, how do we test that? Okay, now let me tell you this. When assumption is violated, we don't need a test statistic that involve a pooled covariance structure. But when the assumption is not violated here, where there is homogeneity of covariances, then we're going to use a T-square formula that actually contain pooled covariance structure. Now, the non, in a one-way analysis of variance, we have G numbers of groups. And of course, sigma 1 here is a covariance for group 1. We're going to have covariance for group 2, and so on like that. Under the assumption, we actually want to test whether they are equal against at least any two is not the same. Now, if we want to test this, we're actually going to use the idea of a wiki lambda, the likelihood ratio test. Okay, and that very approach now is this. The test statistic for the test is this guy here. Take a look at that. Lambda Okay. Oh my God. If you take a look at the SK is going to be a particular covariance matrix for a particular group. And what about SP? Take a look at this. There's W here. Don't forget yesterday we talked about the W that we call within variation. Okay. So before you can get the SP, that is a pool covariance matrix here, you actually need to first get your W, which is the within variation. Okay. Now, the moment and don't for and you know what? This guy here is a product sign. Okay, that guy, that's a product sign. Okay, so which means, and you actually, if you look at the ratio here, it's like a generalized variance that you've done before. That's going to be the determinant of that. Okay, now, the next thing that we're gonna have, okay, this test is according to Judge Box. Okay, and we realize that, okay, you know what, the Judge Box enable us to see that if I compute my wiki lambda here and I take the log and I multiply by -2, that we follow chi-square distribution. Okay, because we actually need a distribution if we were actually want to figure out what the critical value is. Don't forget, I need a critical value before I can take a decision using the test statistic. Okay, so and you can see that is approximately 1 over 1 minus u. And what is u? This is the expression for u. Okay, expression for you. P is the number of variables that you in each group, and G is the numbers of groups that you're comparing. Okay, of course, N is the number of observation in general, and K will be the number of observation in a particular group. That makes sense? And of course, V in the chi-square, if you take a look at the chi-square, the degree of freedom is V. Then I need to be able to determine that V. Oh my God, look at that. V. So U and V here are actually depending on P and G. Okay, they're depending on that. So I needed to pay attention to that. Okay, hold on 1 second. Okay, now I want to move right now, but how do we do this in R? This has been programmed in R. You need to load a package. Okay, library bio tools. Then the moment you have, what is so funny? The moment you have your data X, oh my God, we call this test a box M test. The moment you have your data X, data matrix X, okay, and you indicate that categorical factor, okay, you automatically, the moment you do box M that, you're automatically going to have your p-value. Okay. Now, you're just going to compare the p-value with the level of significance or the level of significance. Okay. So if you take a look at this p-value now, okay, this is less than 0.05, then it means you're actually going to reject. You're actually going to reject. Okay. So we reject the non-hypothesis because of this p-value. Okay. And the moment you reject the non-hypothesis, then it means your previous MANOVA result will be invalid. It's just like, entertaining a case in a district, in a court without having a territorial jurisdiction. Okay. So, the motivated analysis of variance we conducted the other time, we took a decision. We rejected the null hypothesis. We took a decision. From there, we even walk into conducting multiple comparison tests. Everything was so fine, but all of that we're doing remain null and void. Why? Because assumptions underlying the use of the approach that we were using, that approach assumption is not met. When assumption is not met in using a statistical technique, of course, whatever decision you take we should be declared null and void. That's why what make models to be fantastic is when assumption hold. Let me tell you this. Some of the tests may be sensitive to, like I also said here, M test is sensitive to non-normality. So it may be okay to proceed with MANOVA in some cases when M test rejects the non-hypothesis. Okay? Because even the test that we are conducting itself, the box M test that we are conducting also sensitive to non-normality. It's just like how can we actually um, you know, investigate to see whether those who judge us, they are also in the right standing to judge us. They too, they can commit error. That's what we mean. They also rely on some assumption too. Okay. Now I'm going to move right now. We now want to move into two-way ANOVA. The one we did the other time is one way, but um, we we're going to start from univariate. Okay, we look at univariate, understanding univariate. Then we actually going to have an extension on that, and we now consider multivariate. Now, uh, in the univariate, when you have two-way ANOVA, I'm going to use the example that I used the other time. Maybe I'm looking at the effects of two categorical factors. I'm looking at the effects of fertilizer type, um, maybe the light condition. Fertilizer type has three levels: non, organic, and chemical. And light condition, low or high. I want to look at the effect on the plant height, the plant growth, and the measure is the height. Okay, but in a two-way ANOVA, I am actually having two variable. I this is what I want to do for univariate remainder here. I'm only looking at one response, but two categorical factor. One response, two categorical factor, and that's why you see this. Okay, X follow normal. Okay, and the two-way ANOVA model, I'm actually going to have two treatment effects. One for factor A, the second one for factor B. Okay, don't forget we have two categorical factors. Okay, and we're also going to have an interaction effect because the moment you have two factors, there's going to be interaction effect. What do I mean by interaction effect? Interaction effect is this: if the effects of one factor on the response depend on another factor. Okay, and of course you're going to have error. Okay, now now this is the overall mean. Okay, like I said, main effect for factor A, main effect for factor B, and of course the interaction. And we have an assumption for them. Assumption is that, the sum of that have to be equal to 0. Don't forget, we normally want to test treatment effect equal to 0. Okay, now I'm actually showing you two-way analysis of variance now but okay, now we also have decomposition of response variable. I remember I showed you the decomposition of response variable in one-way ANOVA. We also have the composition in two-way ANOVA. So this is actually saying we're decomposing, the particular response into the overall mean, the treatment effect for factor A, the treatment effect for factor B, the treatment effect for interaction, and the error. Okay? So, and of course, each of these, you can see the definition here. Okay? So the treatment effect is when you subtract the overall mean from the group mean. Okay? Now, now, if I want to, I can also decompose the sum of square, the total variation in two-way ANOVA. Okay, if I want to decompose this total sources of variation in two-way ANOVA, I'm going to decompose into the one that can be explained by factor A. Okay, the variation that can be explained by factor A, the variation that can be explained by factor B, the variation that can be explained by their interaction, and finally, the unexplained. Okay? So what I'm trying to tell you right now, please pay attention. What I'm trying to tell you right now is that all of this one, they are the explained variation. Explained variation. Okay? So the first one, the one explained by factor A, the one explained by factor B, and the one explained by their interaction. And of course, this guy here will be unexplained variation. So what we're trying to do is analysis of variance for two-way ANOVA. We enable us to decompose, the total sum, the source of variation into various components. Okay, the one that can be explained by factor A, the one explained by factor B, the one explained by interaction, and and the unexplained. Now, we know this one for conventional, and of course we have a ANOVA table. Don't forget for two-way. Okay, for ANOVA table. Okay, factor one, factor two, the interaction. Okay, and we're also going to have the degree of freedom, and these are the sum of squared. Okay, now, and what hypothesis are you testing? You're actually going to have three set of hypotheses. Okay, uh, the one for factor A, okay, and you only reject H naught if that is greater than the F, okay, and the one for factor B, and the one for the interaction. Okay, all of this is for univariate. Okay, now what we're going to do right now, can we have a way to extend this to want to have a multivariate version? In the multivariate version, I want to look at the effect of fertilizer type, okay, uh, light condition. I want to look at the effect of two categorical factor on three responses. Maybe the first response, plant height, the root weight, then the numbers of leaves. We have more than one response variable, and that will make it multivariate. We're going to call that two-way multivariate analysis of variance. Why is it two-way? Because we have two categorical factors. Why is it multivariate? Because the response variable is more than one. The plant height, the root weight, and the numbers of leaves. Okay? Maybe our focus is on plant growth. Now, this is going to be model for the two-way. It matches from, okay, so many variables are involved. And this is the decomposition of the vector. This is going to be a vector. Okay, don't forget. We're decomposing we're decomposing the vector, the vector x. The vector x contain the plant height, the root weight, and the numbers of leaves. I'm just assuming three variables. Okay, we're decomposing that into the gram mean, the treatment effect. Maybe this guy here is the treatment effect for the first factor, the fertilizer type. Maybe this one is the treatment effect for the light condition, and this is the treatment effect for the interaction, and this is the error. Okay, now we're gonna go into the, oh my God, this is a two-way MANOVA table now. You can see all of that in matrix form. It's like we were rewriting the univariate form in a matrix form. So that's why we have this guy right now. So this is in a matrix form. And of course, this is the sum of square product for total variation. We decompose into the one factor A can explain, factor B can explain, the interaction can explain, and the unexplained. Now let's look into the testing. Okay, I need you to pay attention now. This is where we come. Okay, how do we uh, perform hypothesis testing on the first factor, maybe fertilizer type? Then this is a condition. VA multiply log of that, the wiki lambda, if it is greater than a chi-squared. And what is the wiki lambda? The wiki lambda is this guy. And don't forget, the SSPE, where is the SSPE coming from? And where is the SSPA coming from? Okay, if you go back to the ANOVA table, the SSPE, okay, okay, so if you take a look at this guy, it is what you get here. The one for the error. Okay, this guy actually point to the interaction. This guy, that is the sum of square for factor 2, which you're going to use that one. And this guy, oh my God, that will be for factor 1. Okay, so pay attention to that. Now, right now, let's go. This is the first one. And you know that here, your test statistic is this guy. And the VA, okay, you need to first use this to get VA. Then after getting the wiki lambda, you take the log, you multiply, then you compare with the chi-square before you can take a decision regarding the H naught. Now that's going to be for factor 1. You do the same for factor 2. Okay, this is for factor 2. You do the same for interaction. Okay, in each of these, more than one variable is involved. Okay, now how do we do this? How do we do this in R? Okay, now there's an example here where the variables, the response variable, look at the response variable, there are 4 of them. Okay, we got 4 response variable, and the 2 categorical is cylinder and transmission. Maybe cylinder is factor 1, transmission is factor 2. We want to look at the effects of cylinder type and transmission type on the response. And there are 4 variables. Okay, now using the wiki, these are the code, the wiki. Okay, if you use wiki, okay, so right now, okay, we take a look at this result. Okay, this result will enable you to see, okay, the p-value for the factor 1, the cylinder, okay, is that. The p-value for transmission is that, and the p-value for the interaction is that. Okay, so that you'll be able to take a decision using the p-value, comparing the p-value with the level of significance. So it's like here, they've been able to save you a lot of time going manual, doing all of this, okay, using formula, okay, if you really want to, you're using R, okay, with R, okay, you're just going to get your results, okay. So right here, you can see, this is when we're talking about with interaction. I think we can also do that without interaction because the model can proceed in 2 ways. This is the one that talk about when interaction is involved, and this is the one. And why is it that I want to go from when interaction is involved to without interaction? Because when I look at the p-value associated with the interaction, the p-value is higher than the level of significance. So which means I don't need interaction model. Okay, I don't need interaction model. I actually need two-way multivariate analysis of variance without interaction. How do I know? Because when I included interaction, the p-value associated with interaction is greater than 0.05 significance level. And because of that, okay, that's why I don't need interaction. And let me tell you this guy, you see the code without interaction, it's just going to be your matrix X that have the responses, you're regressing that on cylinder and plus transmission. Okay, but the one with interaction, okay, the one with interaction, okay, you're actually going to see is going to be a multiplication sign. Oh my God. Do you see this multiplication sign? Okay, that is for the one with the interaction. The one without the interaction is going to have a plus sign, okay, which make it a additive model. Okay, and of course, do you know that the other time when we were conducting one-way multivariate analysis test, when the null hypothesis is rejected, we normally proceed to further analysis to know where the difference lies. Okay, where we consider pairwise comparison test, right? We also, because we want to know where the difference lies, we're also going to conduct that with the two-way multivariate analysis of variance. Okay, now I'm going to show you now, and I need you to pay attention with the one for two way. Now with the Beff-Ferroni correction, now you know we have two categorical factors. Now cylinder has three levels, and because of that, we're going to be comparing it two at a time. And that is why you have three comparison, comparing cylinder, engine with four cylinder with engine with six cylinder. And of course, based on what we're seeing here, the difference that exists lying between four and six, because we are from positive to positive, and between four and eight, there's a difference, statistical significant difference. We know we're referring to the MPG, the variable MPG, because you're actually going to do that one at a time. You're going to do that for all the variables. So here I'm only showing for MPG. You're also going to show for other variable as well. And after, of course, there's no statistical significant difference between the engine with six cylinder and eight cylinder, because zero lies, okay, in the interval. Now, can somebody tell me, for extra credit, why is it that in the second factor, don't forget, this one is just for the first factor. Now for the second factor, okay, don't forget we're still on MPG. Okay, don't forget we're having two categorical factors, the transmission effect. Can somebody tell me why do we only have just one comparison for extra credit? Why do we have one comparison, one pairwise comparison for transmission factor, and where for the cylinder we're having three comparison, but for transmission we only having one comparison? Can somebody tell me why? Can somebody tell me why? Yeah. Transmission is actually having two levels. Okay, if it's having two levels, the number of pairwise comparison will be the degree of freedom for two levels. That is 2 minus 1, and that's why you only have one. Does that make sense? Now, but here, we're having this 1, 2, 3, okay? Because initially, we have three levels of transmission of cylinder effect. Is there any question? Okay, so that is where, oh my God, that will be the end of that. And I think I'm going to be reserving the material that I uploaded before multivariate or linear regression for next week. Is there any question before I go today. Any question? Okay, tomorrow is the anniversary or Independence anniversary. Make sure you enjoy your day. Okay, but for now, everyone.